Satu dah. Okay. Good day lah. Okay, robotic system. Introduction to robotic. So, this subject will focus on robotic arm. Robotic arm. Mobile robot will be elective subject. Will focus on the moving robot. But this subject will focus on robotic arm. So you have three three experiment. You have three laboratory. Okay, first regarding this robotic arm, do-bot. Second, you have intelligent mobile robot. Actually, intelligent mobile robot is to introduce or to give you knowledge regarding how to program a microcontroller to interface with actuator, servo motor, and to interface with input sensor. Input sensor is we have here is ultrasonic sensor and infrared. So it's slightly different with robotic arm, but it's more toward interfacing program. So you learn how to interface few type of sensor with microcontroller and how you control your servo motor to drive the robot. Servo motor is related to your robotic arm also lah. So robotic arm normally they use a servo motor or stepper motor to control the arm. So because we have mobile robot, so we use that mobile robot in our lab session. The last one laboratory is using MATLAB. So you will simulate your robotic arm trajectory using MATLAB. So MATLAB, this lab maybe you can do in our lab or you can do it in your hostel. If you have a MATLAB inside your laptop, so you can run it at your hostel. Okay, in this chapter, so you have about 4 or 5 chapters lah. This is introduction, and then we go for kinematic. Kinematic will take quite a long time. We take about 5 or 6 weeks to complete kinematic, because kinematic you have two method lah. One is homogeneous transformation metric and the other one is DH method. So DH, based on theoretical, he said that DH is simplification of homogeneous transformation metric. Homogeneous transformation metric, we use 4x4 metric, and then we just multiply between the metric. So the process calculation is longer lah. DH method, they try to simplify, so we can calculate shorter compared to homogeneous transformation metric. But to develop DH parameter table, you need to do to have a good imagination of 3D lah. So that one, if you fail or you make a mistake to imagine, so you will get a wrong DH parameter table. Then when you develop your formula, you will get a mistake during your calculation. Then you have a trajectory chapter. Trajectory is for your, if you learn how to control your velocity, speed, and acceleration, position, position, velocity, and acceleration of your robotic arm. Then you have a robot work cell topic. Before that, you have a sensor, robot sensor. So you have 4 or 5 topics in this robotic class. Okay, in this topic, introduction. So this is the content of your introduction. Overview of robotic, history of robot, classification of robot, robot component, robot degree of freedom. So degree of freedom means that the flexibility of the robot lah. So for example, in this type of robot, you have 1, 2, 3, 4. 4 joint. That means you have 4 degree of freedom. 4 degree of freedom. So more degree of freedom, that means your robot is have more flexibility lah. More flexibility. Robot joint. So robot joint, this is joint. The part that can be rotated, we call joint. So the part that can be rotated or can move, we call joint. Some part is move linear. So linear motion is different. It's also a joint. Robot coordinate and frame. Okay, this one related to kinematic. Workspace. Robot workspace is a robot working envelope. That means the definition said that the robot can reach, the maximum robot can reach is a robot workspace. So that means if you have a longer arm, robotic arm, so you have a bigger workspace lah. Ataupun or robot working envelope. Some they call robot working envelope. Resolution, accuracy and repeatability of robot. So this is important before you decide to buy any type of robot. So you need to consider these 3 items. So resolution, accuracy and repeatability. So the higher resolution or higher accuracy or higher repeatability, so the cost will be higher. Normally lah. But we have now in the lab a do-bot robot. We have higher resolution, but the price is quite okay compared to the industrial robot, which is maybe more than 10,000 or 20,000. But now we can get about 7,000. But with a good accuracy and repeatability. So this do-bot robot can do laser engraving and also 3D print. So if the robot can do 3D print, that means the robot has a good accuracy and repeatability. And also resolution. Then advantage and disadvantage of the robot. Advantage of the robot. Robot application. Robot application. So, what is robot? So, robot is a machine capable of carrying out a complex series of action automatically, especially one programmable by a computer. So, there are many definitions. So, this is one of definition. And then what is robotic? Just now is robot. What is robot? What is robotic? So, the study of robot, the branch of technology that deal with the design, construction, operation, application of robot. That one is robotic. Robot is robot lah. Robot is a physical of robot lah. So it's one type of machine that capable to do a complex series. A robotic is a study of robot. Okay. And then this is definition of robot based on the ISO, International Organization for Standardization, ISO. So there are 3 definitions of robot, which is a manipulating industrial robot is an automatically controlled, reprogrammable, multi-purpose manipulator programmable in 3 or more axes, which may be either fixed in place or mobile for use in industrial automation application. The robots include the manipulator, including actuator and the control system, hardware and software. Then definition number 2, a robot system is a system comprising robot, any factor, any equipment, device or sensor required for the robot to perform tasks, and any communication interface that is operating and monitoring the robot, equipment, sensor, as far as this peripheral device are supervised by a robot control system. And third, robot is the practice of design, building and applying robot. Robotics. Robotic. So there are many definitions, but definition is just for your knowledge. It's not inside our examination. Okay, this one example of history of the robot. So we take about how many minutes? So you can look at this video.
Robots clean gutters, vacuum floors, wash our windows, dance for our amusement, make for incredibly clean pets, and have even been roped into teaching our kids. Suckers. But well before Fritz Lang's Metropolis, a world full of robotic assistants had already captured the human imagination. Greek myths of Hephaestus say that he built the giant bronze guardian towers for King Minos, a Minotaur thing. As mechanical clocks became more common in the 15th and 16th centuries, automatons flourished and found homes in everything from religious services to drinking age. These aren't robots in the modern sense of the word, sure, but it's a pretty clear line from Alan Turing's elaborate 12th century hand-washing machines to the Roomba that cleans your floor without human interference. By the 19th century, Charles Babbage was creating machines capable of performing complex mathematical calculations.
Ini komputer zaman dulu.
Tesla imagined militarized swarms of his teleautomatons armed with warheads. This violent vision, combined with the growing intelligence of machines like Babbage's difference engine, posed a moral dilemma. Isaac Asimov was inspired partially by that looming danger and the science fiction tales of Adam Lincoln, the self-aware robot, to write the laws of robotics. In 1950, Alan Turing explored the growing intelligence of robots further by outlining a test that could determine when a computer had learned to think, just like a human.
You make up these questions, Mr. Holden, and write them down.
Meanwhile, robot research marched forward. Okay, shuffled forward. Or rolled.
He automatically runs home to her kennel, but charging out.
Anyway, by 1964, robots had found their niche on the factory floor. The Unimog was the first of the industrial robots, and General Motors put it to work on the assembly line, leading the way for human-free manufacturing. The 1960s were a golden age for fictional robots. But more importantly, a pioneering era for computer science. The Stanford Research Institute built Shaky, the first robot that was able to understand and navigate its environment. And MIT had its own artificial intelligence darling in Eliza, an early example of natural language processing that eventually inspired Siri.
Show my photos from last June in San Francisco.
Oh yeah, But in the 70s and 80s, as the recession set in and factory automation meant less jobs for low-skilled workers, the popular representation of robots turned bleak. Dystopian visions of a future where robots were our enemy and not our friends become. Maybe a little over the top, guys. But in the 1990s, IBM's Deep Blue supercomputer showed just what artificial intelligence was capable of. It defeated world chess champion Garry Kasparov in their first matchup, though Kasparov's subsequent 3 victories and 2 draws showed the machines just who is still in charge. By 2000, humanoids started to take off. Honda introduced a walking assistant called Asimo that mimicked human form and motion, and with each successive model, it only became faster, smarter, and more human-like. In the past 2 decades, robots have helped humans reach the depths of the ocean and the far reaches of Mars. They can assist in surgeries and even make hazardous jobs safer. NASA's robonauts have been launched into space to help perform dangerous tasks, while on Earth, DARPA's robotic challenges have led to the rise of machines that can help or even replace first responders. These self-balancing, or well, not so self-balancing bots could potentially save lives. While fully functional rescue robots are still a ways out, machines that can make everyday tasks easier have already earned their way into our homes and factories. In 2002, iRobot launched the first automated vacuum cleaner, and a decade later, Rethink Robotics introduced a Curie-faced factory worker called Baxter to perform simple tasks on the production line. Whether these machines will be our iron-fisted overlords or obedient helpers is still up in the air, but for now, their ability to aid and augment our lives is undeniable.
Okay, so this is a little bit history of robotics. So starting from fully mechanical and then adding some electronic part, and the latest until now, then they combine electronic and computer programming, and the latest they include AI, artificial intelligence, inside our robot system. So robot is improving. Their what you call the brain of the robot, using AI, artificial intelligence system. So this is the first of robot yang we can see in the history of robot tu kan. Carpet. Last time they call a robot. And then okay, you see here, 1955. So this is the DH method that we going to apply in our kinematic. So it's generated, this formula generated in 1955. So it's already about 70 years ago. 70 years. So you learn this 70 years mathematical, maybe modeling in this subject. So about 70 years already. Before this is homogeneous transformation metric. And then this guy in 1955, he tried to improve homogeneous transformation metric using his name, I think. This is David Tenberg, I think his name, who are developing the DH method that we use until now. Then 1978, Umar. And then now in 20th century, so we have a working robot, mobile robot, humanoid robot. So a lot is coming on the real AI robot in 20th century. In 2000, year 2000. Before that, all is more on the electronic. Not many AI in the system yet, because last time during my school level, so we don't have computer yet. So in 90, I remember that during secondary school, Form 2, secondary school, that is about 1988. Sorry, 1988. It's somewhere here, 1988. We are introducing this computer in our secondary school. So that's time I'm in Form 2. So we have a computer class in Form 2. But actually we are not doing anything, we just play a game. So the teacher will teach how to develop a simple game inside the class. So 1988. And when I studied in Polytechnic in 1992, so we have computer, but normally will be, it's very difficult to be used because you need to register, you need to pay some fees to use the computer in the hostel. So we have, in the hostel, we have one lab of computer. So any student that going to use computer, they need to register. So, and then the computer is quite difficult to use. It's not like our current window lah. So when you open your computer, you can see window 98, window 10. It's automatically open. Last time the computer is a DOS command. So you need to type CD window, then the window will come out. And then you can save your memory inside a floppy disk. Floppy disk is a soft disk, diskette. Last time we called diskette. So floppy disk. So floppy disk is the first one before they come out HD diskette. So both type of recorded device always have a problem when you save your work, and then after a few days you cannot open it. So then nobody want to use the computer, because when you save it inside the floppy disk or diskette, so after a few days or few weeks, then you cannot open it. So diskette corrupted. So better during our study in Polytechnic, we use a typewriter, so manual typewriter or electric typewriter. It's safe, then you save inside your diskette. So pen drive, we start using in 2005, when I joined in Unimed. So I joined as PLV, teaching engineer. So in that time, the pen drive is coming out. So we start using pen drive. Pen drive is better lah, to save our work. So 2005. So the pen drive that you use now, starting in 2005, maybe 2004, but it's very expensive. 2005, a lot of pen drive coming out. So the size is 256 megabyte. 256 megabyte. It's very small memory, but it's enough during that time lah. It's enough. But now your camera, everything is in high definition ni kan, resolution punya image. So 256 is not supported already. So now you are in 2000 century, 20th century. So we are combination of mechanical, electronic, computer programming, and AI in robotic. So this is come out of mechatronic course lah. Combination of all that topic. Okay, supply of industrial robot. So yang ni sampai 2014 lah, 2014. So everybody can hear my voice?
Boleh,
Yes,
boleh.
sir.
Yes, sir, ya. Boleh.
Okay, this one is 20th century, 2002 until 2014. So estimate worldwide annual supply of industrial robot. So dalam industrial application, so the robot in industry is increasing up to 2014. So you see that number of unit. So 229 plus 000, that's mean 200 to 29,000 unit in 2014. So they use a robot in industrial. But it doesn't mean that when we use a robot, we reduce the labor cost. But actually, we reduce the labor cost. But normally they use the robot for maybe for the area that hazardous. Maybe because of the temperature, high temperature, that human is unable to work for long time, and also maybe because they use for high accuracy or high repeatability, because when they use a human, so their accuracy and repeatability is not accurate as robot lah. So in that area of application, they will use a robot. Same like in automation industry lah. So the highest application of robot in the automation industry. Automation industry, if you see in Proton or any automation industry, you can see a series, a line of robot lah. So they do spot welding, arc weld, MIG welding. So their repeatability is very high, repeatability, accuracy lah. Because if we use human will do cannot perform higher repeatability. They good accuracy, but in certain duration. After maybe 4 hours or maybe 8 hours of working, so their repeatability is will be low. In semiconductor, based on my experience last time, we use a robot in molding a station. So for example, when I work with LED product, so LED, they use a robot. So operator will put the LED frame. LED actually when we do a production in a frame. So one frame contain about 20 or 30 LED in the frame. So after they cut it, after complete the process, then they cut to be singulated. Before they cut, before complete the product, the LED diode, they fabricate on the frame. So when they want to put the LED into the molding machine, so we cannot put one by one. So if you put one by one, and the molding machine is very hot, so if you want to put one by one, so your arm, everything will be burned. So panas, it's very hot. So they make a big frame, and then they put all the LED frame on a big frame, and that a big frame will be transferred to the mold by a robot. So robot will have a lot of advantage lah at that molding station because it's not vibrate, it's not shaking, it doesn't care about the temperature inside the molding, and then we can control the speed. If we move very fast, so you will have a lot of problem on the LED lah, because LED is developed by my semiconductor and a very tiny gold wire, gold or silver wire. So if you shake the frame, so the wire will be turned, bend, or a lot of problem lah. So when you use a robot, so you solve a lot of problem. So that is in semiconductor. Normally, if you see semiconductor, when you want to transfer the product into the mold, normally they use a robot. Because molding is very hot. So if you use human to put something inside, and also it's dangerous. Molding is very dangerous. So a lot of accident. The mold is clamping the hand, so it's dangerous. So if the mold clamp the robot, it's not dangerous to human. So this is estimate worldwide annual supply of industrial robot at year end by industries 2012 to 2014. So which industry is using a lot of robot? So it's automotive industry. Automotive. Why? Because automotive, you need a very high precision and high repeatability. Because a lot of product for automotive we call mandatory. Although you make a screw is mandatory. Because why? Because every part of automotive or car or automotive is affected human life. So we call mandatory. Last time when I work with Agilent, now they call Abago. After that they change to new name, I think. Last time Agilent, then before that HP changed name to Agilent. Agilent changed the name to Abago, and then I'm not sure they changed to what name after that. So when we do a panel for car, that's mean a meter panel for a car. So the meter panel also is mandatory. So we test it using a military standard. So all the car part will be, the spec is a military spec. Because, for example, if your car panel give a wrong result, for example, your temperature or your engine temperature, suppose is too hot, exceed the specification, so you need to trigger the driver to stop the engine, to park or check. But if your panel didn't give a right result until your engine is burned, so the driver still didn't know the engine is burned, so it will affect the human life. So that's why every part of the car is mandatory, and we need a very accurate product, very good quality product in automotive industry. So that's why in industry automotive industry, they use a lot of robotic and automation, robot and automation. Same like tire is very critical, tire screw is very critical, and all the parts is very critical, all they call mandatory. So electrical and electronic, yes, they use robotic, especially if you work with semiconductor, wafer fabrication, in Silterra or Infineon, in Kulim. So So you see a lot of robot lah. They use a lot of robot, especially in wafer fabrication, semiconductor. Because the component, their part is very small, maybe smaller than ants, because the wire itself is 20 micron, smaller than our hair. So you need a robot to do the process. So human cannot do it because the product is very small and very high quantity. So one wafer disk, we call this wafer disk semiconductor, contain more than 100,000 chip or dies, dies or chip on the wafer. So 100,000 is picked up by a human. Sure, you cannot do in one day. Normally, when you use a robot or machine, they can pick up in few hours. 100,000. It's very fast. You can see inside semiconductor production in YouTube. You see how fast the machine or robot do their task in semiconductor product until you cannot see their hand. So it's very fast. Metal industry because it's very hot, high temperature. Chemical, rubber, plastic. This is all because their metal, chemical, because their environment is not suitable for human. Electronic because they need very high repeatability of tasks. Because one wafer contain about 100 chip. So they need a very high production and very high precision. So they use a robot. Automotive because all is very critical, all part is critical. They need very good quality of product because all part is mandatory spec. Chemical, same to the metal, is because of environment, it's not suitable for human. Food, because of hygiene, they use a robot because they need a clean process. This is others. They have the purpose when they use a robot. And then this is service robot in the market. Defense, field, logistic, mobile platform. Defense is military lah. Military. Medical, construction, cleaning, inspection, underwater submarine remote control robot tu kan. Rescue and security, and others. Medical because of hygiene lah. So they use a robot for hygiene and high repeatability lah. So defense, now a lot of robot they use in defense, especially mobile robot lah. So if you open in YouTube, so they say about a small team of military, maybe 10 or 20 army, they have one mobile robot. Something like drone or other type of robot they in that one group. They have few robot in each of their team. Okay, classification of robot. Okay, robot have divided into two. One is stationary, the other one is mobile. So we study in this subject is more on stationary robot. serial robot and parallel robot. And then mobile, we have will also have connected with stationary, because some robot now you can see that they put a robot arm on the mobile robot. They combine. So they put a robot arm stationary on the top of mobile. So your robotic arm can move. And then legged robot, swimming robot, flying, and etc. Some they call amphibia, so they can walk in the ground and also they can swim or they can dive in the water. So they call amphibia. So this robot is focused on industry robot industry application. So what is series and parallel? So we see what is series parallel. So this is serial kinematic mechanism. This is parallel kinematic mechanism. This is hybrid serial and parallel mechanism. But in our class, we only focus on series kinematic mechanism. These two normally did by master level master student. They study on this parallel and hybrid series parallel mechanism. So in our robotic, we are focused on the serial kinematic mechanism. This one. So this one, actually if you understand this, then you can further study on this. Because this is combination of serial. So this one leg of this table is similar to one serial kinematic mechanism. So you have, for example, this you have 5 or 6 serial, then it become parallel mechanism. So it's more complex, complicated. So we learn in our robotic class only serial kinematic mechanism. Ini pun dah mencabar. This is also already tough for us to imagine the 3D imagination. If you combine maybe 4 or 6 serial mechanism, it's more complicated. Okay. Nanti pukul 2 kita berhenti sekejap, 5 minit. Sudah kita sambung balik. Lagi berapa minit? 4 minit. Okay, classification of industrial manipulator. Okay, manipulator in our subject is robotic arm. Robotic arm we call manipulator. Okay, so how we class the industrial manipulator? So we class based on the power source, application area, method of control, and geometry. So if we want to purchase a robot, so we need to consider these 4 main items. So first is power source. So if you want to use in a very clean environment and very less noise, so we will use a electrical power source. Electrical power source. Cheaper, clean, and quiet. Cheaper, clean, and quiet. Normally, we use this robot in semiconductor product in a clean room, kan? Clean room industry or medical industry. So we use electric source. Electric source. So if we need a very strong power, but doesn't care about the noise, then matter about the response, because hydraulic is very slow response. So we can use hydraulic because its response is very slow, torque very high but noisy. And then the other one is oily. So a lot of leakage. Normally in hydraulic system, you have a lot of oil leakage. So normally it's not suitable for clean room environment. Pneumatic is fast compared to hydraulic, noisy, but sometimes we use also a lot. We use also in our semiconductor product in clean room, because it's a clean system, but it's only have a noise. Noise can be filtered. Some they use a noise filter in pneumatic system. If they use in industrial semiconductor industry. Because why? Because pneumatic is simple system and also fast and quite strong. And then the application area. What process do you want to do in the area application that you want to use in the area? So for example, you want to use for painting or welding or material handling. So different type of robot will do different tasks. For example, painting or welding, we will use articulated robot. Articulated robot because you have more joint. That means, for example, you have 6 degrees of freedom. So your robotic arm have good flexibility for tasks such as painting and welding. And then because painting normally you need a very flexible, same as human hand. So human hand can be very flexible. So you need a 6 degree of freedom. So one type of robot that have a good flexibility is articulated robot. Pick and place, normally they use a SCARA robot. SCARA robot, normally they use for pick and place task. Welding, articulated robot. And also some they use spherical robot also they use for handling pick and place. And then what control do you want to use? Method of control. So you use a servo or non-servo robot. For example, if you want to do point-to-point or continuous pass, this one is point-to-point, for example, is spot welding. So you want to do a spot welding, point-to-point. Or you want to use a continuous something like MIG welding. So you need to do a continuous welding, non-stop. So that one, the method of control. Geometry. So geometry, arrangement of kinematic chain, serial, articulated, cylinder, spherical. This is the we call working envelope or workspace of the robot. So geometry. So what geometry? If you have a small space or you have a big space, so you need to decide the geometry of robot. So this is classification of industrial manipulator. So based on these 4 items for deciding the type of robot that you going to choose. This is robot system. Example, robot system. Oh, tuduh lah. So kita break 5 minit. We break 5 minit lah. Ada lagi dalam separuh lagi lah. 10 slide lagi. Kalau mana-mana yang awak nak tanya, awak boleh tanya. Okey. So ni robot yang awak akan guna dalam awak punya lab. So nama dia robot. Robot magician, magic magic. So yang ni yang awak akan session ni boleh buat lah dua-dua lab, simple je. Cuma kalau awak nak buat program dalam Python semua tu ambil masalah kan. Tapi yang ni kita guna teach pendant dia. Kita guna teach point ni. Kita tekan button ni. Kita boleh teach dia. Ataupun awak boleh guna GUI dekat dalam PC lah. Robot dia. Robot magician. Motor dia guna servo tak silap saya. Drive dia guna metal ni, metal shaft ni untuk drive. So berapa sendi kita ada? Satu join. Okay, motor ni untuk satu motor untuk join pertama. Di bawah ni boleh pusing satu join. Ni satu boleh pusing ya. So the first motor for join 1, join 2, join 3. So the 3 join lah. 3 join. So 3 join boleh we can cover 3 axis lah. Nanti ya. So this one lah. A new robot. So nama dia robot magician, terbalik dia punya tulisan robot magician. Okay. So kita start boleh. Okay, robot system. Kita tengok. Ni kita panggil one set robot system lah. So robot system ataupun or in our next chapter, maybe chapter 4. So we learn about robot work cell. So this is one work cell. So this is one type of work cell. So for example, this is a manipulator. Manipulator is a robotic arm. Manipulator is a robotic arm. So sambut dia call manipulator, sambut dia call robotic arm. So this is camera. So camera will take for in this case maybe they use a camera to as a sensor to detect the product. The product will go through this conveyor, move through this conveyor. So the camera will capture the image of product and then send to PC. PC will do image processing and make a decision. So this robot controller actually to control the robot motion. So to control the robot motion, and then the motion the instruction will be given by PC. PC will send the instruction to the robot controller to control the robot motion. Robot controller is similar to motor driver lah, something like that. But because a robot controller, they have maybe something like special for this robot, something like AI, everything inside this. So PC will send the signal to move the robot through a robot controller. For example, this one, sensor, they send through PLC. PLC will send also the signal to robot controller to inform that maybe the part is coming at this conveyor. So send the signal to robot for the robot pick up the part. Maybe pick up from this conveyor and place to this conveyor. Something like that. PLC normally they use to control the conveyor belt and then to interface the sensor signal. They use a PLC. PC more on vision system, we use a PC because last time PLC cannot make a decision on image processing. Maybe the latest one, they already put computer inside the PLC. Maybe they can do image processing. But currently, more image processing will be conducted inside a PC. Robot control is just for controlling the robot motion. That's all. So the instruction to move the robot, everything come from PC and come from PLC. So inside robot control, they have something like that we're going to learn. Inside this robot controller have a DH method, program, calculation, or maybe they use a homogeneous transformation metric formula inside this robot controller. So all the motion of the robotic arm use that method calculation. Whether they use DH method or homogeneous transformation metric. Because you want to move from point to point, for example, from this point to point A to point B. For example, here is B, point A to point B. So to move from this A to B, we need an algorithm. We need the formula, something like DH method or homogeneous transformation metric. Because why? Because you have many joint here. You have 1 motor, 2 motor, 3 motor, and 4 motor maybe. So you have 4 motor to control the robotic arm in the same time. So you need to move the robot in the same time from point A to point B. So to make a decision of that, so you need algorithm inside this robot control. So inside this, you have homogeneous or DH method lah inside our robot control. PC just said move to point A, move to point B. So but PC doesn't care how you calculate. So all the calculation will be done inside robot control. Actuator, a lot of things lah. Actuator, maybe this conveyor drive or motor to drive the conveyor, we call actuator. Sensor, this is sensor. Controller, so you have robot controller. Processor or computer, this one lah, PC. Software, so you have software in the PC, or maybe you have software also inside PLC and robot control. So if you have this complete system, so we call robot system, or we call it a robot work cell. End effector, what is end effector? End effector is a gripper of robot or maybe welding tip, drill that we attach at the end of robot arm, sorry. So we at the end of robot arm we put tool, so that tool we call end effector. For example, this tool may be a camera, so we put a camera at the end of robot arm, we call end effector. Okay, so this is the mechanical structure of the robot arm or manipulator. So this part we call arm. This one you need to remember. This part we call arm. This we call wrist. And the tool that you attach to the wrist we call end effector. So this tool you have a lot of tools like gripper, suction cup, drill, welding tip. Every tool that you attach at the end of your robotic arm we call end effector. For pick and place something like this, we put a gripper. Or maybe you put a suction cup. If you want to drill something, to drill a screw or to drill a hole, so you put a drill, so that drill we call end effector. If you want to weld, do a welding, but normally this type of robotic arm, difficult to do a welding because their joint is insufficient. It's not flexible. How many joint you have? 1, 2, 3, 4. So if you want to going up, if you want to going down, no, you cannot rotate it. You only can rotate in this side, but you cannot rotate the other side. So it's difficult to do a painting process. So they use this for pick and place process. So this is arm, this is arm, this is wrist, this is end effector. So this is joint. So for example, you have this is joint, joint 1 in the bottom, joint 2, joint 3, joint 4. So you have 4 joint. 4 joint, that means you have 4 degree of freedom. 4 degree of freedom. So between joint, link between a joint we call link. So we call a link. So this part we call link. Link because link between joint. So now you are going deep and deep. Okay. Okay, mechanical structure of a robot manipulator consists of a sequence of rigid body, link. So between this we call link. Interconnected by means of articulation, joint. Okay, so you have joint here. So between a joint we call link. A manipulator is characterized by an arm that ensures mobility, a wrist that confers dexterity, and an effector that performs the task required of the robot. So an effector is a tool. But an effector is not joint. It's not considered to increase degree of freedom. So an effector is a tool. It's not joint. This is open kinematic chain. This is closed kinematic chain. Closed kinematic chain is similar to the parallel mechanism. But in our subject, we not focus on this parallel mechanism. So we focus on open kinematic change, robotic arm or manipulator. Okay, robot joint. So this is the type of robot joint. We have 5 types of robot joint. So if the drawing is square or like this, we call prismatic joint. Prismatic means that we move linear direction, with the X direction, Y direction, or Z direction. So that one we call prismatic joint, or P. Short word is P. This type we call revolute. Normally you found this type of revolute joint at the bottom part of robot lah. So for example this one. So this part is robotic revolute joint. This also revolute, but the drawing is slightly different. So you see the first revolute joint is this part. This one. But in our robotic arm cannot turn 360 degree because have limitation at the encoder system. Normally, maximum the robot can turn or rotate is 270 degree because the sensor that we put at the robotic arm, the limitation is about 270 degree. Cannot turn 360 degree. This also revolute joint, but this is you can find it at the robotic arm joint. This one or this one. So still revolute, but the drawing is slightly different, mechanical drawing. You can see here. So this is revolute at the bottom side. This revolute at the arm side. But the symbol is the same lah, R. And this one is a universal joint, U. And this is spherical joint. Universal and spherical. So this is the formula is slightly different. So in our study in robotic, we are focusing on these 3 types of joint because we use a robotic arm. When we use a robotic arm, so we focus on these 3 types of joint. Okay, degree of freedom. What is degree of freedom? Degree of freedom, number of independent position variable which would have to be specified to locate all parts of a mechanism. In almost manipulator, this is usually the number of joint. So the important thing to remember is easier lah. So degree of freedom is how many number of joint. So if you have 3 joint, that means you have 3 degree of freedom. Darjah kebebasan. In Malay language, darjah kebebasan. So if you have more joint, that means you have more degree of freedom. Means that your robot is higher flexibility. But if you design a robot, if you have more degree of freedom or more joint, so that means you need more motor to drive. More joints means that it's a motor. So if you have more joint, you have more motor. So if you have more motor, that means your robotic arm is heavy. Because once you want to develop a strong robotic arm, you need a very high torque of motor. So high torque of motor is very heavy. So when it's too heavy, so it's very difficult to get successful design. So normally when you see the robotic arm in the market, if they design it, the robot, same as this type of robot, they put the motor, everything at the bottom to make it a light to reduce the weight at your arm. So they put all the motor at the bottom or at the base, because if you put the motor at the arm, so your arm will be you have a very high weight lah at your robotic arm, so it's not accurate as something like what? Something like a Parkinson robot lah. Your robot cannot move smoothly because your arm is very heavy. So they put the motor, everything, the heavy part on the bottom side. They drive the joint using a mechanical. Whether they use a steel rod or they use a timing belt. So from the motor to the joint, they use a timing belt or they use a metal rod to drive. So they try to minimize the weight of the arm. That's why this robot can perform 3D print, laser engraving, because the arm is all the heavy mechanical they put at the bottom, so the arm can move very smooth lah. In the most general case of tasks consisting of arbitrarily positioning and orienting an object in three-dimensional 3D space. 6 degrees of freedom are required. 3 for positioning and a point and the object. 3 for orienting the object in the respect to the reference coordinate frame. Okay. To perform tasks like a painting, process, application, so you need at least 6 degrees of freedom of robotic arm. 6 degrees, that means 6 joint. 6 joint. Because you need a very flexible of your robotic arm or manipulator. If you only use 3 degrees of freedom, normally they use for painting. Pick and place task. For painting, they need a very flexible robotic arm. Same go for welding. So they need a very flexible robotic arm. So minimum is 6 degrees of freedom. If more degree of freedom than tasks variable are available, the manipulator is said to be redundant from a kinematic viewpoint. Okay, this means that if you require 6 degrees of freedom, flexibility, for painting tasks, you purchase 8 degrees of freedom. So the other 2 degrees of freedom is we call redundant waste. So suppose you need to use a 6 degree of freedom is sufficient for painting process, but you buy a robot that contain design with 8 degrees of freedom. So we call redundant, so it's not used. Okay, before this we learn about joint. So this is type of robotic arm. This is joint that we learned before this, slide before this. So 3 P's mean that 3 prismatic joint. Prismatic, that means you move linear direction or straight direction. So for example, this joint move Z direction. This joint move linear in X direction and this joint move in Y direction. So this is prismatic. You move in linear motion. So if you have this 3P mechanism, joint or robot design, so actually you are, I jump to this slide time before, you are using a rectangular workspace of robot. So this is the working envelope or workspace of robot. So if you use this 3P or Cartesian robot, we call Cartesian robot, that moving, that have a 3 prismatic joint. So your working envelope will be like this, a square shape. Square shape. But doesn't mean that if you use a square shape, you cannot produce a round shape of product. You can produce also a round shape of product. But here it shows that the maximum or the working envelope that you can, this robot can produce is, the maximum that robot can produce is a square shape. But if your product need a round shape, within this, yes, the robot can perform. Same like you purchase a 3D print. 3D print is a prismatic joint, X, Y, and Z, but you still can print a curved shape of product. So a curved shape of product, something if you want to print a ball, a spherical ball. So you want to print a ball, so this robot still can print, if you put a 3D print nozzle at the end of this machine, so it become a 3D print, so it still can perform. It still can perform every shape within this working envelope, because this is only working envelope. This is the maximum this robot can perform. But any shape he want to perform inside within this shape, this robot can perform. So you can print maybe a ball, you want to print maybe what we call teddy bear, you want to print, so you still can print. You can print it. This is working envelope. If you want to show that the maximum working area that this robot can perform the task, the maximum. So within this, the robot can perform. This is cylindrical. Cylinder. So Cartesian is a square. Cylindrical is cylinder. So the working envelope shape is cylinder. So because cylindrical robot. So the working envelope, the maximum this robot can perform, the shape is a cylinder shape. So 2 R2P, that means 1 revolution, rotation, revolute joint. So 1 revolute joint and 2 prismatic joint. So this is rotate here, perform a cylinder shape, and this going up and down, Z direction, axis, and this is maybe Y or X axis. So when you move the robot can will perform this cylinder shape or workspace or working envelope. So this robot also can perform any shape within this working envelope. Okay, this is a spherical robot. That means 2 revolute, 1 prismatic. So this is revolute, 1 prismatic, linear. So you can extend and retract. This arm can extend and retract. This part is end tool. This is end tool, maybe gripper. So this one, what shape can be generated by spherical robot? So this shape will be generated by spherical robot. So you have 1 rotation, 2 rotation, and 1 linear motion, prismatic. So this is spherical robot. It's slightly different from this articulated robot. So spherical, you have more space that cannot be achieved. But articulated robot, your arm can perform better and can reach up to the top level area. So it's more flexible compared to spherical robot. Very good. So this is articulated robot. 3 up, rotation, rotation, rotation. So your robot working envelope become like this, where the working area is bigger compared to spherical robot. And the last one is SCARA robot. Normally SCARA robot they use for pick and place. They have 2 rotation and 1 prismatic. Same like this. 2 rotation and 1 prismatic. Normally they use this for pick and place. This robot that we use it in the molding machine in semiconductor factory. So they use SCARA robot in the molding station, molding process. So what it look like? So this is the working envelope or workspace of the SCARA robot. And this is joint and link representation. So this is Cartesian robot. This is spherical robot. This is spherical. This is cylindrical, articulated, and this is SCARA. SCARA robot. Okay, all these value, for example, theta 1, theta 2, theta 3, this value will be included into our kinematic formula lah, homogeneous transformation metric or DH method. So we only use angle, theta, and also the link length. So the link length, same like this one, theta, pi, and the link. The length can be extended. So this value, 3 value will be, 6. For example, this is 6 value will be attached inside our algorithm to find the point from maybe you want to find DH or homogeneous transformation metric we want to develop. So we will include these 6 variable into our metric. So this one similar to working envelope lah. You use Cartesian, you can perform this. Maximum shape is like this, cylindrical like this, spherical, and articulated, and SCARA. So better use this one. So this one. Okay. Now it's robot characteristic. Robot characteristic. There's a 4 items that we need to consider when we want to choose the robot. So we need to know the payload, reach, precision, and repeatability. So if we want to purchase the robot, we need to know also what payload that we required the robot to pick up. So maybe you want to pick up a very tiny chip. So then we need, we doesn't need a very strong robot lah. So the other one, reach. Reach, that means it's a working envelope lah. Working envelope or workspace. So what is the distance between point A to point B? So you need to decide the length of your robotic arm. And then precision. Precision means that, for example, if you want to move your object from point A to point B, so how precise? Normally they say 0.01 mm, for example, precision. So the higher precision, the higher price we need to pay. So we need to decide what precision that we require for our task. And then repeatability. Repeatability means that is related to precision, but if you move the robot 100 times, if the robot able to put the object exactly at the point A and point B, so we call that very high repeatability. High repeatability. So if your robot cannot put at the same exactly point A or point B after 100 times, so that means that your robot is low repeatability. So you need to, maybe your process doesn't require very high repeatability or not very high precision, then you need to decide whether that robot is sufficient enough for your task or not. So if you need a very high precision and high repeatability, then the price will be higher. But this robot that we do bot magician that you will use in the lab session, the precision is 0.01 mm. It's very good precision. That's why this robot can perform 3D print and also laser engraving. Okay, we introduced a little bit about kinematic. So next week we will start kinematic because I already discussed with Prof. Abu Hassan. So he will take the class regarding sensor after Hari Raya. So I will take this kinematic about 5 or 6 weeks until after Hari Raya. So now we have about 3 weeks before Hari Raya. So I will take this topic about 5 or 6 weeks, kinematic. And we have one assignment. Maybe next week I will give assignment title. And maybe one quiz lah before Hari Raya. I'm not sure we will discuss later with the lecturer. So when supposed to do a quiz. So this is kinematic. So up to here, any question or not? Sunyi je.
The question, Doctor.
Tak ada lagi teori je kan. So nanti kita tanya banyak dekat ni lah. Regarding the kinematik. Kinematik nanti banyak kena tanya. Sebab nanti susah juga kinematik ni. Killer topik lah kinematik. Killer topik. Okay, this one is just introduced to kinematik. So you can see here. So this is your robotic arm have 4 joints. 1, the base, 2, 3, 4. So you have 4 joints. So the first joint we call world reference frame. So W is world reference frame. So why we call world? Because this is the world of this our calculation robotic system, robotic arm. So this is world point, world reference frame. So we must have reference. So we cannot refer to this product. This is part, because this part will be moving. This box also will move in the working envelope. So this box will move in this robotic arm working envelope. This cylinder also will move. So we cannot use this reference as a world reference. World reference means that everything in this part will refer to this reference. Same like if we use compass, if we walk in the world, so we use a compass. So compass will refer to the north pole. If we not refer to the north pole, you cannot calculate your longitude and latitude. You cannot decide your position. So everybody will refer to the north pole. So in this calculation, in your robotic calculation, so we must refer to the base of your robot arm. We call that point as a world reference frame. So this is the world of the robotic arm. So we refer at this point. Because others point, reference frame will move. So this joint will move, this joint will move, this joint will move. So we cannot refer that joint as your world reference frame. So we must refer at the joint that fix, that not move in the system or in this robotic arm. So E is an effector reference frame. So this is an effector reference frame. So for example, we see here Z is vertical. So you can see your an effector reference frame. Z is slightly slanted to the right. So that means there are certain degree here change. That's why your reference frame at your gripper change from your world reference frame. So how many degree? So we use homogeneous transformation matrix to calculate. You see why? So y before this is horizontal. Now y is slightly changed, going up. X also change from this position, this axis to this axis. So how to find this angle? So to find this angle, you need to use homogeneous transformation matrix or DH method. So this angle change because why? Because changing of this joint. So this joint change a little bit. Before this is straight, So now he turned to the right and join number 2. 1, 2, 3. Join number 3, turn to the downward. Join number 4, a little bit downward. So that's why you get this reference n effector reference frame. The angle is different with your world reference frame. C, reference frame at the cylinder. So this one is your part. For example, your robotic arm going to pick up this cylinder to put somewhere, or to pick up the square box to put somewhere. So, for example, if you work in the industry, so you want to pick up some part, so that part have an orientation. So have an orientation. So you need to capture using a camera, check the orientation of your part, and then you need to turn the part to your required position. So you know, now you already know based on your camera, so you get the information that your part, your X direction is this way, Y direction this way. So it's slightly different from your world reference frame. So now you know that you can calculate, you know that, X is maybe 30 degree. Orientation is slightly shift 30 degree or minus 30 degree. So you can see that X is this direction and this X this direction, the world. So we refer to this X, so we know that the orientation of cylinder orientation, the current cylinder orientation. Now you can manipulate your robotic arm to pick up your cylinder and turn to your required position based on the information from the camera that capture the image of the cylinder. Same go to the square box. You can see the X and Y. Y is same direction, but X is slightly different. So now this information actually comes from the camera, capture the image orientation, inform the robot. So the robot now know how to manipulate the object because he know already the orientation of the object. But all this frame is referred to the world frame. Where is the world frame? The base of the robot. So we must have a world frame to calculate. If you don't have any reference frame, so we have difficult to find the orientation or to decide the orientation for pick and place. What is JI? J is joint, I is a variable. That means how many joint you have. If this joint 1, this is joint 2, this is joint 3. That means this is J3, joint 3. So you just make it JI because I will be depend to the number of joint. For example, this is joint 1, joint 2, joint 3, joint 4. So we have frame 1, frame 1, frame 2, frame 3, frame 4. Frame on each joint. So it's not so difficult, but you need a very good imagination on 3D. Okay, now we go to slide 26 already. So at least you have, I hope you have an idea a little bit to